Now let's solve this problem. It says use node voltage to find VO. Now where is VO in this circuit? Well, we know VO is the voltage across this 2K resistor, right? So we're going to be using node voltage in this particular problem to find for the value VO. Now because we want to use node voltage, the first thing we must do is label our essential nodes, right? So we know this is going to be an essential node here. We know this is an essential node here because it has 3 or more connections. This is also an essential node. This is an essential node. And this node right here is also an essential node. Now when we look at this, we usually take the bottom node to be our reference node, right? Now we usually take the bottom node to be our reference node because that is the node that usually has the most amount of interconnected elements. Now when we look at this, we actually have an even amount, except for one node which is in the middle that has 4. So really this has the most connections, but we won't take this to be our reference node. Now you can choose which one you would like to be the reference node, but in this particular situation, because they want us to find the voltage VO, which is the voltage across this 2K resistor, I'm actually going to take the reference node to be this node here. Yes, this node, right? It's going to be crazy. Crazy. But I'm going to take this node right here to be our reference node. Okay, so I'm going to label this V1, right, which is the voltage at node 1. I'm going to label this node right here V2. I'm going to label this node V3, which is node 3, but the voltage at node 3. And I'm going to label this node 4, but the voltage at node 4. So now we have the right node voltage equations at these particular nodes. Now because they want me to find the voltage across this 2K resistor, right, I'm just going to start writing the node voltage from node 1. So we're going to have node voltage at node 1. By the way, I'm not sure where to start, but I'm just going to assume that I can start at node 1. You can label these different, by the way, okay? You don't have to choose this to be node 1. You can choose this to be node 2. You can choose this to be node 1. This is just the approach I'm taking for this particular problem. You may not choose this node to be the reference node. You may choose this node to be the reference node. So it's really up to you how you want to proceed with this, but this is how I'm proceeding with this one, all right? Now, we're just going to follow the steps. We know we're going to assume current is leaving this node. So because we have a current source that's going to be entering, we're going to write this as a negative current. So we have negative 4 times 10 to the negative 3. Plus, we have the currents leaving this node in this branch. We're going to say V1 minus V3 over 2000. Now we have another current source that's going to be entering this node here. So we're going to treat it as a negative current. So we have plus negative 2 times 10 to the negative 3. All of this is going to equal 0. So we want to get rid of this 2000. So we're going to multiply each term by 2000. That's going to give us negative 8 plus V1 minus V3 minus 4 equals 0. Therefore, we're going to get V1 minus V3 equals positive 12. So this is going to be equation 1. We have V1 and V3, and these are our two unknowns for this particular node. Now let's do node voltage at node 2, right, which we're going to assume is right here. So we have node voltage at node 2. We're going to have the current leaving this node, which is what we want. So we're going to treat it as positive, right? So we have 2 milliamps plus, we want to assume the current is leaving this node going in this direction. So we're going to have V2 minus V3 over the resistance, which is 1000, right? So we have 1000 plus the current leaving this node coming this way. It's going to be V2 minus V4, right? Because we actually took this essential node and we wrote it as node 4. So we have V2 minus V4 over 2000. All of that equals 0. So when we simplify this now, we're going to get 4 plus 2V2 minus 2V3 plus V2 minus V4 equals 0. Okay? So when we simplify this, we're going to get 2V2. We're going to get 3V2 minus 2V3 minus V4 equals negative 4. So this is our node voltage equation at node 2. So I'm going to label this equation 2. Now let's do the node voltage at equation 3, right? So we're just going to keep writing this out. I know it's a lot, but we'll get there. We have the current coming into this node. So because it's coming into the node and not leaving, we're going to treat it as negative. So we have negative 1 times 10 to the negative 3 plus, we can assume the current is going this way, right? Which is going to be V3 divided by 1000. Because of our reference node label here. Then we have V3 minus V1 over 2000. And we have one more current to write, which is going to be the current in this particular branch. We're going to take the voltage difference, V3 minus V2 over 1000. All of that equals 0. And when we simplify this, we're going to get negative 2 plus 2V3 plus V3 minus V1 plus 2V3 minus 2V2 equals 0. So we're going to get negative V1 plus 5V3, actually hold on, minus 2V2 plus 5V3 equals positive 2. Now let's do the node voltage at node 4, and then we'll solve for the unknowns from there. So you have the node voltage at node 4. We're going to have a current source leaving, which is going to be 1 milliamp. So we have 1 times 10 to the negative 3 plus we have V4, and because this is the reference node, it's going to be V4 over 1000 for the current in that branch. So we have V4 over 1000 plus, and we know that's the current in this branch here, V4 minus V2 divided by 2000. So we have V4 minus V2 divided by 2000. All of that equals 0. So when we simplify this now, we're going to multiply each term by 2000. So that's going to give us 2 plus 2V4 plus V4 minus V2 equals 0. Therefore, we're going to get negative V2 plus 3V4 equals negative 2. Now, when I look at this, I have a bunch of unknowns, right? I have V1, V3, V2, and V4. So I have 4 unknowns and 4 equations. Of course, we can use a matrix to set this up. But the thing is, in my calculator, the highest matrix I can write is a 3x3 matrix, right? So because that's the case, I'm actually going to have to use some substitution. So I'm going to look at this and I'm going to say, you know what? Which equation is going to be the easiest for me to simplify? So when I look at this, I can either use equation 1 or equation 4, right? Now what I'm going to do is I'm actually just going to use equation 1. And I'm going to use equation 1 and substitute it into one of these equations That way I can eliminate one of these equations. So I can say V1, right, equals 12 plus V3. So everywhere I see V1, I can just write 12 plus V3. Now there's no V1 for node 2, but there's a V1 for node 3. So what I can do now is I can actually substitute in V1, which we know is going to be 12 plus V3. So when I do that, I'm going to have negative 12 minus, right, negative 12 plus V3 minus 2V2 plus 5V3 equals 2. Therefore, we're going to get negative 2V2 plus 4V3 equals 14. Okay? So this is our updated equation now. Now, because we don't have any more, we can just move on from there, right? Now, when we look at this, we have, so we're not going to be looking at equation 1 anymore. We're going to be looking at equation 2, 3, and 4, right? So we have 3 unknowns and 3 variables. So we're actually just going to use matrix method. So I'm actually just going to use the matrix method now. So I'm going to write this out as, I know, one big matrix, right? So this is a lot, but we'll get through it. I'm actually first going to write our unknowns, right? Which is going to be V2, V3, V4. Now for the first equation, which we're going to take as node 2, we have 3 for V2, so we have 3. For V3, we have negative 2. And for V4, we have negative 1. And all of that equals negative 4. Now for equation 2, which we're going to take at node 3, we're going to have negative 2 for V2. Now for V3, we have positive 4. And because there's no value for V4, we're going to write it as 0. And all of that equals 14. Now we're going to do the node voltage at node 4. We got negative 1 for V2. We have 0 for V3, but we have positive 3 for V4. And all of that equals negative 2. So we're just going to use our calculators now and perform matrix multiplication. So we're going to take the inverse of A multiplied by B. And what answer do you get? When we solve for this, we know V2 equals 1.4 volts. V3 equals 4.2 volts. And V4 equals negative 0.2 volts. Okay? So we have successfully found the voltages at these nodes. Of course, we can find the voltage V1 because we know V1 equals 12 plus V3. Therefore, V1 equals 12 plus, we just found the voltage at node 3, and that's 4.2. So we get 4.2. So we know V1 equals 16.2 volts. Now, they don't want us to find V1. They actually want us to find the voltage VO. So how do you think we should find the voltage VO? Well, think about it. It's going to be between these two nodes, right? Which is V2 and V4. So to find that, we're actually just going to subtract. So to find VO, we're just going to use this equation. VO equals V2 minus V4, because we're going to assume, because the terminals are labeled positive to negative here, that the current is going to flow in this direction. So we're going to subtract the two voltages to find the voltage V0. So let's solve for this now. We know we're going to use the equation. We're going to say V0 equals V2 minus V4. V0 equals V2, which is 1.4 minus negative 0.2. So when you solve for this, V0 equals 1.6 volts. So this is going to be the voltage across that resistor. V0 equals 1.6 volts. Now this problem was a lot longer than the ones we have done so far, but if you can answer these types of problems comfortably without watching the video first, then you are well on your way. So if you need help, rewatch this again, leave a comment down below, and I'll be sure to get back to you.